Section 12.6, Triple Integrals in Cylindrical Coordinates, Video 7. This is question number 22 out of the homework section. You can find it on page 735, but you won't see anything aside from what I've written up here. And for full disclosure, I haven't worked this problem out yet. I kind of have a visual of how it's going to set up, but I haven't written anything except what you see. So what you're about to see is a cold attempt at a triple integral in cylindrical coordinates. You know, like you would do on your homework or on your test. All right. One thing I do want to mention though is that we're being asked to find the volume of a solid, and I don't think I mentioned this previously, but this is kind of an important yet simple concept to understand in calculus. When you do a triple integral over a solid of just dV, that gives you the volume of E, because the integral of dV is just V. Similarly, if you do a double integral over a region D of dA, that gives you the area of A. The equivalent in one dimension is if you do a single integral over an interval from A to B of dx, that gives you the length of the integral. Interval. So there's a really simple underlying principle that recurs whether you're in 1, 2, or 3 dimensions, that if you do an integral of either dx, dA, or dV, it gives you length, area, and volume. Length of an interval, so one-dimensional measurement of a one-dimensional object. Area of a surface, two-dimensional measurement of a two-dimensional object, or volume of a solid, three-dimensional measurement of a three-dimensional object. So this is a simple yet important underlying concept to know. And in this problem, it's also going to help us set up our integral. So we already know that the answer to our problem is going to be the triple integral over the solid dV. But in order to write this as an iterated integral, you know, 3 in a row as opposed to one object, a triple integral is equal to 3 individual integrals. We need to describe the solid, and probably in cylindrical coordinates, namely because we're still in the section on cylindrical coordinates, but one of our surfaces is a cylinder. Now the other one's a sphere, but it's still got the x squared plus y squared, which is just screaming polar coordinates. All right, so let's sketch the solid and see what it looks like. The cylinder x squared plus y squared equals 1. We could turn that into polar coordinates or cylindrical coordinates really quickly. X squared plus y squared is equal to r squared. So this is the same as r squared equals 1. And if we square root both sides, we could just say r equals plus minus 1, which is kind of redundant because if we're going to say a radius of 1 and draw a circle, then saying a radius of negative 1 says point that way but walk backwards. But either way, we would get the same circle. So we can just say r equals 1 and we'll get the same equation. Over here, however, we have x squared plus y squared, so that's r squared plus z squared equals 4. So now I know what a sphere looks like. This is a sphere, its radius is 2, it's centered at the origin. It's just like a circle except in 3 dimensions. But when it comes to converting the integrals and limits of integration into cylindrical, we're going to have to take advantage of this equation. All right, so let's see what the solid looks like. We have a cylinder whose radius is 1. So let's set up. Actually, let's draw the sphere first because it has a larger radius. It has a radius of 2. So if we go out 2 spaces on each axis, I guess we should go backwards too. Then our cylinder, let's go 2 spaces on the x and y axes to draw the intersection of the cylinder with the xy plane, so it's a circle. And then it goes up 2, so we can just draw some quarter circles on each axis, so it almost looks like a baseball cap, if you will. You may have noticed in past videos, whenever there's a line in the back of an object, I'll draw it dotted like that. So there's our sphere, or at least the top half of it. Maybe I should draw the bottom half as well. 1, 2. So let's just connect everything. Okay. guess we should connect back here also, to be fair. Okay, so there's our cylinder-looking sphere. Now let's draw the cylinder. The cylinder just has a radius of 1. And again, this is a cylinder because that's the equation of the unit circle on the xy plane. Makes no mention of z, so the z can go anywhere. So unit circle up and down makes a cylinder. But the unit circle is half as big as the projection of the sphere onto the xy plane. So we shoot a cylinder up here and down here. All right, so it's almost like somebody's taking, well, think of it this way. You ever cored an apple before, where you have that little metal cylinder that you shove down the middle of an apple to take the core out? That's kind of what's going on here. For convenience, our apple is a sphere, and we're shoving this cylinder right down the middle, and we're pulling out the core. So we're looking to find the volume of this thing. So let's cut the sphere, the cylinder, and let's erase the part of the cylinder that's outside of it because it's getting kind of messy. There's no kind of to it, it's already messy. All right, so we've got this cylinder, and here's the top of it. So I'll shade that in kind of solid. And the bottom of it is down here, down somewhere. We don't know where these intersect yet. So here's the bottom of the cylinder. Let's see. I'm sorry, bottom of the sphere. It almost looks like a pill. Okay. So let's see if we can define this messy, messy, messy picture in terms of cylindrical coordinates. We know the top and bottom are bounded by the sphere, and the equation of the sphere is this. But we want the top and the bottom surfaces defined as z equals something. So we should probably solve this for z. That's easy. Move the r squared over. So z squared equals 4 minus r squared. And then take the square root. But here's where you have to be careful. When you square root both sides of an equation, technically you need to use a plus minus. Recall that I did over here and then argued that I really didn't need both of them, because whether your radius is 1 or -1, when I spin around, I'm going to get the same circle. So it's redundant to say r equals plus or minus 1 there. But here it's not redundant, because we need to think about the positive z's and the negative z's. So because z equals plus minus the square root of 4 minus r squared, we can safely say that the top of this solid is the equation z equals the square root of 4 minus r squared. And we say that the bottom is z equals the square root of 4 minus r squared. Excuse me, z equals negative square root of 4 minus r squared. Now, what is the projection of this into the xy plane? Well, since it's encased in the cylinder, the projection is just going to be this in the xy plane. So the surface over which we'll evaluate the double integral is just the unit circle, which in polar coordinates, the r is between 0 and 1, unit circle radius is 1, and the angle theta can make one complete revolution from 0 to 2 pi. And that will give us the entire disk that represents the surface in the xy plane. So I think this is going to be pretty easy to set up. Let's start with dz. And the z's are bounded below and above by these equations. So negative square root of 4 minus r squared, positive square root of 4 minus r squared. Now for the double integral, dr d theta, because it's in polar coordinates, we do pick up an r. You'll see why that's not only convenient but necessary in a moment. And then our r's are going from 0 to 1, and our thetas are going from 0 to 2 pi. So this will actually be a pretty straightforward integral. You may be worried that the first integral has square roots in their limits of integration, but as you'll see in a moment, that's going to actually be pretty easy to overcome. I think I'll pause this video, start a new one to evaluate this.